Hello viewers, in this video I will discuss about Gauss law. Before talking about Gauss law, we should know about the term electric flux. If you have not known about the term electric flux, so in this video description I have given the link which describes the introduction of the term electric flux. So please have a view of it and then come to this lecture. Okay, so now we'll see what is this electric flux. Okay, so you know that electric flux. So it is given by, this is flux, as it is electric flux, it is given by phi e. Okay, so which is equal to E vector dot A vector, which is written as EA cos theta. Theta is the angle between the electric field and the area vector. Okay, so now let us consider a charge plus Q. So which is enclosed by a spherical surface, which is enclosed by a spherical surface, which is enclosed by a spherical surface like this. Okay, so now let us consider a small area element. Let us consider a small area element dA. Okay, in which the area vector will be pointing in this direction, outward directions, because you know that area vector will be in outward direction for the 3D surface. Okay, so electric field will be also in this particular direction due to this charge. Let us take the distance as capital R. Okay, so see here the E and dA, the angle between the two components will be 0. Okay, so you know, so let us take the electric flux component as very small component. So d phi E, which is equal to E vector dot dA vector. Okay, so this could be written as E dA cos theta. Theta is 0, so this is E dA, that is d phi E. So we have found the value for this d phi E. So now what is the total flux for this total spherical surface? So that is the closed surface, because it is a closed surface. So it includes the total flux is closed integral of this d phi, which is equal to closed integral of this dA, which is equal to, let us now take E as a constant for this particular surface. So we have Q placed at the center of this charge. We see that whatever may be the area surface, see they are separated by distance r. So the electric field will be constant. So if this is the surface chosen, so it will be r. If this is the surface chosen, r. This is the surface chosen, r. So due to this charge, we see that at all the points, we see that the electric field remains constant. Okay, so here we are taking the electric field as constant. Okay, so E closed integral of dA, which becomes EA. So the phi E becomes EA. Okay, so phi E is written as EA. So you know the value of electric field. See, from Coulomb's law, we see that the value of electric field due to this charge plus Q is given by Q by 4 pi epsilon naught R square. Distance r. Okay, so this A is total surface area. See the total surface area of a sphere, you know the formula, it is 4 pi r square. So when you cancel 4 and 4, pi and pi, r square, we see that the flux formula is now changed to Q by epsilon naught. This is the expression we have got to express the Gauss law. Okay, so what this formula? This formula, okay, this is a mathematical formula which is used to find the value of electric flux, but this is the expression given by Gauss in this law. So what this law says, we see that the Gauss law, what is the statement given by Gauss law? He says that the net electric flux through a closed surface is 1 by epsilon naught times 1 by epsilon naught times the net charge net charge enclosed by the surface. This is a statement given by Gauss law. Net electric flux through a closed surface is 1 by epsilon r times the net charge enclosed by the surface. If I have many number of charges means net charge enclosed by the surface. This is a statement given by Gauss law. Okay. So by giving this statement, Gauss law has also given some conditions, some important points by using this Gauss law. So we will see what are the points given by Gauss. Okay, we will see one by one. Okay. So some important points is given by Gauss. What is the first point? Total electric flux through the closed surface. Total electric flux through the closed surface is 0 if no charge is enclosed by the surface. Okay, we see that the total electric flux through the closed surface becomes 0 if no charge is enclosed by the surface. Okay, so let me explain the point with an example. So now let us consider a cylindrical surface. Okay, now we see that no charge is enclosed inside the surface. Okay, so now I am going to place this cylindrical in an external electric field. Okay, so that electric field is produced by any external source charges. Okay, so that from outside external charges. Okay, we are keeping in this electric field may be uniform or non-uniform, whatever may be the case. Okay, so now let us consider the cylindrical parts. Cylindrical, we are dividing into three parts. This, let us mark this point as 1, this point as 2, and this surface as 3. Okay, see, like this. So here we have a cylindrical surface. See, let us mark this as 1, this as 2, and this particular surface as 3. Okay, so now we are going to find the electric flux through the separate surface. We know that electric flux is equal to EA cos theta. So for the first one, here we see that, see, the electric field is pointing in this direction, but the area vector, as it is a closed surface, we see that the area vector should point in this direction. Okay, so the angle between E and A now are 180 degree. Okay, so here it is EA cos 180, which means that phi 1 is equal to minus EA. So phi 1 is equal to minus EA. Similarly, we see that phi 2, see, in case of phi 2, the area vector is pointing in this direction. So E and A are parallel to each other. So they are parallel to each other, and the angle also is theta 0. Okay, so cos 0 is 1, so the value of phi 2 is EA. In case of third section, we see that the electric field is going in this direction, the area vector is in this direction. The angle made is 90 degree. You know the cos 90 is 0, so phi 3 becomes EA cos 90, so phi 3 becomes 0. Okay, so what is the net flux? So net flux is equal to, when you add all this, we see that minus EA plus 0, which becomes 0. The net flux becomes 0. So here it is proved that the external charges has no contribution to the flux inside your closed surface. Okay, so if no charge is placed inside the closed surface, there is no value of flux at all. So the total flux remains 0. This is the first point given with respect to Gauss law. Okay. Okay, we'll move on to the next point. Second point. Gauss law is true for all closed surface. Yes, yes. Whatever may be the shape and size. Whatever may be the shape and size. Now see that we have already found the expression for Gauss law by considering a spherical in which a charge is enclosed here. We know that the radius is r. So if the value of r is r, we have derived based on this particular condition. So if I have the same charge placed inside a sphere of radius 2r, if this is the case, so let's see what happens to the value of the electric flux now. So you know that it is EA. So the electric field due to this charge at this particular point will be equal to, that is Q by 4 pi epsilon r. Distance is 2r square. It becomes 2r square. Normally it gets reduces because as the distance moves, we see that the value is reduced. Okay, fine. So what happens to the total surface area? Total surface area also becomes 2 pi into 2r square for this particular area. Okay, so this cancel, 4, 4, 5 cancel. We again come back to the same expression Q by epsilon naught. Okay, so from this we see that whatever may be the size, whatever may be the size increasing or decreasing, the value Q by epsilon naught remains the same. Okay, so what happened to the shape, different shapes? So for different shape, if we even consider different shape, even for this shape also we are getting the value of phi q by q naught. Okay, if you are considering a cylindrical surface having a charge q here, so the flux for this also q by epsilon naught. Okay, similarly if I have a conical structure, if I have a charge q here also it becomes q by epsilon naught. So whatever may be the shape or whatever may be the size, the Gauss law expression remains the same. It is valid. Gauss law is valid, whatever may be the shape and size. So this is the point given in this particular statement. Okay. Okay, now move on to the third one. Third point. The value of Q net, see this is Q net actually, net electric field, okay, net charges, sorry. Q net in the Gauss law is only the net charge enclosed by the surface. Only the net charge enclosed by the surface. So it means that, see that if I have a closed surface like this, if I have charge here Q1, Q2, and if I have a charge Q3 outside, so here we see that the formula of electric flux changes as, see this Q net is only the charge Q1 plus Q2 by epsilon naught. So this is a statement given here. Only the net charge enclosed by the surface. Okay, only the net charge enclosed by the surface. No external charge contribution towards the net charge. Okay, so this is the statement given in the third point. Okay. Okay, now we'll move on to the fourth one. Okay. If we have charges inside and outside the surface. See the uh, the the electric field. The electric field is electric field will be due to all the charges. Due to all the charges, both inside and outside. Both inside and outside. See, if we have a arrangement like this, we have Q1, Q2 and Q3 outside. See, the electric field will be due to all the charges, because you know all the charges will produce electric field. So the electric field that is in this formula, you know that this is equal to E into A. This electric field in the electric flux formula will be the electric field due to all the charges, both inside and outside. See, the electric field will be due to this charge, due to this charge and due to this charge. So we have to consider the electric field due to all the charges. But when we consider the net charge, we see that it is only the charges due to inside the surface. But while considering electric field, it is due to all the charges. What are maybe the number of charges? Okay, so this is the major point to be considered. Okay, fine. Okay. Next, fifth point. So in case of fifth point, okay. Closed surface in Gauss law is called as Gaussian surface. It is called as Gaussian surface. Okay, fine. Now, so we have discussed that if we have a charge Q placed at the center of a sphere, we see that it is a symmetry at all the points of the surface. Okay, so what happens when I keep, you see the electric field will be symmetry at all the points. Okay, so what happens when we keep a charge plus Q here, we see that the electric field varies, because we know that the electric field is inversely proportional to distance square. So we see that the distance due to the all the surfaces will be different. So electric field will be variable. Okay, so in such conditions it is very difficult to find the expressions. Okay, very difficult to use the Gauss law. So for easier calculations, okay, so for easier calculations, you have taken certain assumptions, or you have taken certain statements. For easier calculations, see, for easier calculations, Gaussian surface, the Gaussian surface should be symmetric. the Gaussian surface should be symmetric about the charge distributions. So among the should be symmetric among the about the charge distributions. Okay, so this is the first point to be considered. Okay, the charge distributions may be, in most cases, let us consider it as continuous charge distributions. Okay, when compared to discrete charge distributions, it is more preferred to consider it as continuous charge distributions for easier calculations of your Gauss law. Okay, next we have the electric field. See, the electric field should be same. Electric field should be same at all points on the Gaussian surface. Next, the third one, the theta. See, the theta should be same at all points on the Gaussian surface. Okay, these are the points to be considered. And one more point with respect to Gauss law, we see that is a sixth point. So these are points considered for easy calculations. So one more point, if we continue with respect to fifth and sixth, we see that the Gauss law and Coulomb law are related. The Gauss law and Coulomb law, they are related. Okay, so we see that we have obtained this formula by applying this expression. Okay, if we again, we know that flux is equal to EA, which is equal to Q by epsilon naught. So EA is equal to Q by epsilon naught. So if I apply E 4 pi r square, which is equal to, so from this E again we are getting it as Q by 4 pi epsilon naught r square. Okay, so we are getting the value of this electric field with respect to Coulomb's law. Okay, so from this statement, see that Coulomb's law and Gauss law and Coulomb's law, they are related and they always follow inverse square law. They always follow inverse square law. If it is not accepted, means they are against the inverse square law. It means like that. Okay, so this is the final statement which is given in the Gauss law condition. So these are some of the points discussed in with respect to Gauss law. So we have seen the expression for Gauss law and we have also seen some points to be followed when we apply the Gauss law. Okay, thank you.